Alright, so today is June 30th. We're almost done with June. That's kind of exciting, right? We're almost done with the semester. Are you guys excited or not really? So, okay, so not really. I'm kind of excited. So let's start. I'm gonna turn off my video because we're gonna be on OneNote. So this is what we did last time. So I'm just gonna briefly go over and then take over from what we left off last class, and then we'll start our class today. So we finished 3.6, which was another method to solve non-homogeneous differential equations for constant coefficients. And today we're gonna do spring problems. So we derived the formula for a spring problem last class. So I'm just gonna briefly go over that. So here we're gonna do 3.7 and 3.8 together, because 3.7 is just setting up the spring problem homogeneous, meaning there is no external force, and 3.8 is when we start adding external force to it. So we have a spring of natural length L, and we add a mass to it, so it stretches the spring some length of big L. So big L represents the spring, the length of the spring is stretched. And once it is stretched, we kind of look at the equilibrium position. So that's where we call it the 0th position. And then from there you can either pull the mass downward or compress it upward. If you pull it down, it's positive. If you compress it upward, it's negative. Okay, so that's important to keep in mind. And then we start noticing that if this is the scenario, if that's the system we're working with, we have a gravitational up force that's working on it. We have a spring force that's working on the system. And sometime we might add a damping force to it. And so we have Fg, Fs, and Ft. And we might also add an external force to it. So that's G of t. So along with all of this, by applying Newton's law, I don't remember which law this is, probably the second or the third. I don't really care the numbering, who cares? We know the law, that's the good point. So we know that the sum of all forces acting on a system is equal to mass times acceleration. So that's how we got this formula. Well, if we use calculus, we know position, you can label it as a function of u, of t. And then if we take the first derivative of any position function, we have the velocity function. So that's u prime of t. And then if I take the second derivative of the position function, or taking the derivative of the velocity function, you have the acceleration function. And then by replacing that into this formula, we have sum of the force equal to ma. A is the acceleration, so we replace that with mu double prime. And then what are the forces acting on the system? Well, we said we have a spring force that's pulling the spring upward, so it's negative. We have a damping force that's also acting against gravity upward, and then we might have some external force, that's G of t. And then putting all of these together in a nice formula, we have moving f of s to the other side, moving f of d to the other side, we have mu double prime plus f sub d plus fs equal to some function G of t. And then we redefine what is the external force, what is the spring force, and what is the damping force. So that's when we came up with this formula. So we said that the damping force is a damping constant times the instantaneous velocity, which is u prime. So we have gamma times u prime. So that's what I replace f sub d with. And then a spring force, well, we know from calculus 2, or calculus, let's just say from calculus, we know this. Which 2, I don't know. There's so many changes in the department, so let's call it calculus. So we know spring force is determined by the spring constant k times the position, which is u. So we have negative k times u. That's going to stand for spring force. So replacing that into our formula, we have k times u equals to G of t. That's the differential equation we're working with. along with the initial conditions. So we have initial position and initial velocity. Because it's second order, you need two conditions to solve for your unknown constants. So we have u of 0, initial position of the mass, u prime of 0, which is the initial velocity of the mass. Now, the big question is, how do we find these unknown constants, m, gamma, and k? So we have force that we are familiar with is the weight is equal to mass times g. And from here, we can find m, which will be the weight over gravity. G is the gravitational constant. So we can use either 9.8 or 3.2. And then we can also let weight be equal to K times L, which is the spring force, and L is the stretch. And we can find K by dividing it by L, so we have K is equal to W over L. And gamma, we can find it by using the formula resistant force over velocity. And sometimes the question might give it to you, but it's good to know how to find it just in case it doesn't give you what the damping constant is. Alright, so having said that, that was all last week. Now we're going to do an actual example. Okay? So let me know if you guys have questions. So here for today, I typed some question up so that we can use it and I don't have to write it. So I typed them. So I spent some time typing these questions. Took me a while, not too long, but I think it's worth it. Okay. So we're using, so I'm just going to rewrite it one more time, the formula. So we're going to use the formula m times u double prime plus gamma times u prime plus, so this is still 3.7/3.8, just in case you're wondering. And then we have k times u is equal to some function g of t along with u of 0 and u prime of 0. So these are the equipment we need to solve this differential equation. Okay, well, to set it up. Sometime you might be setting it up, sometime you might be solving. Okay, so for the first problem, so let's read this and see how much we can digest. So this is example 1. And I'm just going to move this on the bottom because we don't need it right now. Okay. Okay, so let's see what's given to us. We have a weight of 1/10 Newton stretches a spring 5 centimeter, which is converted to 1/20 meter. If the mass is set in motion from its equilibrium position with the downward keyword velocity of 10 centimeter per second, which converted to a 1/10 meter per second, and if there is no damping, formulate the initial value problem that governs the motion of the mass, then determine at what point or what time does the mass first return to its equilibrium position. Okay, so let's see what can we set up, right? So we want to find our unknown coefficients, which are m, gamma, and k. Set up the differential equation, and then we'll solve for it. So for the first part, we're given the weight, which is 1/10, right? And then we're also given stretch, which is 5 centimeters, so 1/20 meter. So we know big L, that's 1/20. And what else are we given? So there's no damping, so we know gamma is going to be 0. Okay? So let's see. So from here, we can find what is K. Well, K is going to be the weight over gravitational constant G. So we know the weight, that's 1/10. G, so which G are we going to use for this scenario? So there's two constant value for G. So G could be either 32 feet per second or 9.8 meter per second. Square. I think it's square. Meter per second square. Yeah. Okay. So someone tell me which value for G are we going to use? 9.8, right? Okay. All right. So Greg also, right? So this is 9.8. So if I simplify this, this is just 1 over 98. So that will be K. No, sorry. That's M. So first mistake of the day. That's M. Okay. And K is going to be determined by the formula, the weight over stretch. So that would be 1 over 10 over L. That's going to be 1 over 20. So that's going to be 2. Okay. So we have so I think I multiply this one wrong. That should be 98. Yeah. Okay, that looks right now. Okay, and then K is 2 and gamma is 0. So we have the differential equation. So M, that's 1 over 98. U double prime. Gamma is 0, so we don't have the second term. Plus K, that's 2U, is equal to. So the problem doesn't involve any external force, so we're assuming it's going to be 0. Okay. Now we set up the initial condition. Alright, so let me set up my audio again. So let me know if you guys can hear me. Aisha, can you hear me now? Alright, so I hope you guys can hear me now. Alright, so we have the differential equation set up. Now, what about the initial condition? What is the position and what is the initial velocity? So if you read the problem one more time, if the mass is set in motion from its equilibrium position, so we're going to set it motion from the equilibrium position. So that's 0. And with a downward velocity of 10 centimeter per second, so that means it's positive initial velocity because you're applying velocity to it, and it's going to be 1/10 meter per second. So that's the setup for initial conditions. So this will be the answer to the first part, along with the initial conditions. Now for the second part, so I'm going to move these further down. So for the second part, we want to know when will it first return to equilibrium. So let me know if you guys have any questions for the first part of this question. So now for the other half, we want to determine at what time does the mass return to its equilibrium position. So that means we need to solve for it and then see when is it coming back to equilibrium. So if I solve this differential equation, well, it's a second order, constant coefficient, homogeneous, so we know how to solve this. So let's solve. So I'm going to divide or multiply both sides by 98. So that's going to give us, so what's 98 times 2? That should be 196. Yeah, okay. So we have U double prime plus 196 U equals to 0. I think that's right. It looks right. So g of t is 0 because it doesn't mention anything about applying an external force to the system. So we're assuming there is no external force. So g of t is 0. So let's solve it. So we write out the characteristic polynomial r squared plus 196 equals to 0. So r is equal to plus and minus 14i. So complex root. So our solution u of t is c1 cosine of 14t plus c2 sine of 14t. Okay? Well, now we apply the initial conditions and then we can solve for c1 and c2. So we have u of 0 is equal to 0, which implies that, so plugging in 0 for t, sine will go to 0, cosine will go to 1, so we have 0 is equal to c1. So if c1 is 0, then our u of t will be modified to c2 sine of 14t. Okay, so I'm going to move these further down because they're on my way. Let's go down. Okay, so that's u of t. Now we can differentiate u of t. We have 14 c2 sine of 14t. And then from here we can apply the second initial. Yep. Cosine. Hold on. Oh, absolutely. Yep. Yeah, sorry, another mistake. So today is a mistake day again. Sorry, guys. I think I have these very frequently nowadays. The derivative of sine is cosine. Never forget. Right? Yep. Okay, so this will survive. See, if we plug in 0 for t, u prime of 0 was equal to 1 over 10. So that means we have c2 is equal to, So we have 1 over 10 is equal to c2 times 14. So that means c2 is going to be 1 over 10 times 14, so that's 140. So that would be c2. So that means the function that will describe the motion of this mass is going to be u of t is equal to 1 over 140 sine of 14t. So that's the solution we have. Now, if you remember, you're watching a spring traveling up and down, so it looks something like this, right? It's keep going like that unless it stops. So if I were to draw this solution, so it looks like a sine curve, right? So we have an oscillation of sine curve. So if I draw this solution, what is the amplitude? So here's something we should recall. What's an amplitude? Do you guys remember? Right, so the amplitude is it's sort of like the peak, or you can say the height of this graph. So in this case, amplitude is 1 over 140. So I can just say this is 1 over 140 over negative 1 over 140. So that's the amplitude. So if we have a function, say y equals a sine of omega t, or cosine, so let's say b cosine of omega t. Amplitude is a, so amplitude is a or b. So those are the amplitude value. in absolute value, so I should put that in there too. So that's also from pre-calculus. So let's put this as a side note. Now, what about the period? How do we determine period of a trig function? What is the formula? So if you recall, for any sine or cosine curve, period is 2 pi over omega. Omega is the value that's right inside the argument. So in this problem, what's the period? So we have 2 pi over 14, because our omega is 14. So that's going to be pi over, pi over what? 7? Yep. So that would be the period. So Liana, yep, so that's correct. So this function that we have, it's going to complete one revolution, meaning one cycle, from 0 to pi over 7. So imagine the spring is, so now you have to kind of imagine it in an opposite direction, because downward is positive and upward is negative. So instead of having a curve, sine curve going this way, that's not the curve we're going to have. We're going to have a different curve. We're going to have a reflection of that. So this is negative, that's positive. And our solution looks like this, because downward is positive for us and upward is negative. Okay, that's why it's a reversed sine curve. Now keep in mind, it completes one cycle at pi over 7. So when does it first return to equilibrium? So this is equilibrium. So yeah, so that's right here. Half of its period. So it takes half of its period to reach equilibrium. So it reaches equilibrium at t is equal to pi over 14. So a little bit of pre-calculus applied to spring problems. So that's something to keep in mind. Okay. Another thing that you also want to keep in mind is a frequency. Okay, so frequency is also useful. All right, so we answer this problem. So we were able to determine the second order differential equation that will govern this initial value problem. And then we're also able to determine the time when it first reaches its equilibrium position, meaning comes to the equilibrium position. Okay, so let me know if you guys have any question. All right, so let's do the next problem. So here's the next problem I have, number 2. Okay. So let's set up another differential equation. So I'm not going to really solve this one. I think the solving, you can handle that on your own. So I'll leave that up to you to solve. So let's take a few seconds to read this problem and we'll just set it up. Okay, so let's start. So a mass weighing 2 pounds stretches a spring 6 inches. So that gives us a lot. So we have a weight of this much pound and 6 inches is the stretch. And then when t is equal to 0, the mass is released from a point 8 inches below equilibrium position. So that's important, with an upward velocity of this much. So we have to determine the equation of the motion, but I'm just going to set it up. So I'm not going to solve it, okay? But I think solving, you can figure that out. That's just more algebraic skills that you can build up to, okay? All right, so having said that, let's start. So what's given to us? What's the weight? Two, right? So good. So we have the weight, that's 2. And from here we know m is going to be the weight over g. So we have 2 over. Now for this one, because it's feet and seconds, those are the units, we're going to be using 32 for g. So that would be 1 over 16. So that's m. And then we have a stretch after we attach the mass. That happens to be 6 inches. So we can't use inches, we have to use feet. So we have to make sure the units are consistent. Okay, so 6 inches, if you convert that to feet, you have, so 1 foot, 12 inches, right? Yep. So that would be 1/2 of a foot. Okay, and then the question doesn't mention anything about damping. So we're going to assume there is no damping force. So gamma is going to be 0. And then from L, we know what K is. So we can determine the value for K. So K is going to be L. No, it's going to be the weight over L. So that would be 2 over 1/2, which is 4. So that's that. Now let's set up the differential equation. So we have m times u double prime, so that's 1 over 16 u double prime plus gamma is 0, k is 4, so we have 4u is equal to, the question doesn't mention external force, so that's also 0. Along with the initial condition u of 0, what's the initial position of the mass? 8. So we have to convert that to feet. So 8 inches is how much in feet? So if you divide that by 12, right? 2 over 3. Yeah. All right. And then initial velocity, what is that given to be? So we're applying a velocity upward. So we're compressing the spring. So that would be negative, yep, 3/4. So that will be the differential equation we set up. And then again, if you want to solve it, you would go ahead and make the coefficient of u double prime 1 by multiplying it by 16. So 16 times 4, that will give us 64. So u double prime plus 64, u equals to 0, along with the initial conditions. So our solution to this would be by solving this second order differential equation. So I will leave the solving to you, okay? So you can finish me. Okay? So any questions on setting it up? So these problems are free oscillation because there is no damping involved. Once we involve damping, then there's no free oscillation. There's going to be damping. So any questions so far? Okay, so moving on to number 3, if there are no more questions. So again, I'll give you guys a few seconds to read this, and then we'll start. Okay, so let's start. So we have a mass weighing 8 pounds, so we know W is equal to 8. Stretches of spring 2 feet, so big L is 2. Assuming that a damping force numerically equivalent to 2 times the instantaneous velocity. So we're given a damping constant, gamma, which is 2. And acting on the system. Okay, so got it. We want to determine the motion of this mass if the mass is initially released from the equilibrium position with an upward velocity of 3 feet per second. So again, we're releasing it from equilibrium, so that means the position is 0, and initial velocity, it's going to be 3 feet per second upward, so that's -3. So these are the info that are given to us. Now let's find our unknown constants. So we want m u double prime plus gamma u prime plus k times u equals to g of t. Or I think I wrote big G of t for the notation. And g of t is again 0 because it doesn't mention on the problem, so assume it to be 0. So let's go ahead and find m. So m is going to be the weight over g, and the weight is 8. G is going to be again 32 in this problem because we're using feet per second square. So that would be 1 over 4. And gamma we're given that's 2, so we don't really have to solve it. K, we need to solve it, so W over stretch, big L, that will be 8 over 2. So that's 4. Okay, so setting up the initial value problem, we have 1/4 u double prime plus gamma, that's 2 u prime plus k, that's 4 u is equal to 0. And then I'm going to go ahead and multiply both sides by 4 so that we have u double prime plus 8u prime plus 16 u equals to 0, along with u of 0 is 0 and u prime of 0 is -3. So that's the setup for this problem. And then from here, how would you solve this? Guys, how would you? No, I wouldn't use reduction of order. How do we solve second order constant coefficients? Yeah, so you would write out the characteristic equation and then it's homogeneous, so you can either factor or use the quadratic formula. And you will see if the roots are real, repeated, or real, distinct, or complex. Okay, from there you can write out the solution. So any questions on number 3? So again, I didn't finish this. You can go ahead and finish. So that one is also finished me. Okay. Alright, so any questions on these problems? So I have one more to work on. So I'll give you guys a few seconds to set this up. And then we'll do something else. Okay, so does someone tell me how do you guys approach this question? Mm-hmm. So we have, so spring weighs 80 pounds. So we have the weight, that's 80, and we have the big L, that's 6 inches. So we need to convert. So that's going to be 1 over 12 inches, 1 foot. And that would give us 1/2 of a foot. Right, FT, good enough. Okay, so, and then I'm just going to ignore the unit. Maybe I should write it out, right? Yeah. Okay, and so from here we can determine our unknown constants m and k. So we know m is going to be the weight over g, so that would be 80 over 32. That's the value we're going to use for g. So if I simplify this, that's 1/4. Yeah. And then k, it's going to be L, that's L over G, so that would be 1/2 over, oh, hold on, did I? No, I think I didn't do it right. Hold on, go ahead. Mm-hmm. Uh, sorry, I didn't get to hear your question. Oh, yes, it's W over L. That's what I was going to write. Yeah, absolutely. Thank you. So that would give us weight, which is 80 over L. That's 1/2. So that 5 over 2. 80 over 32. Yep, yep. 5 over 2. Sorry. So this will give us 5 over 2. So sorry for my mistakes. Okay. And for k, we have 80 over 2. So if I simplify that, that's 160. Okay, I hope I did that right. Okay, so what else are we given in this problem? Okay, right, so we have a g of t given, that's 5 cosine of omega t. And what else are we given in this problem? So is there any damping force involved? So gamma is 0. It doesn't mention, so we assume it to be 0. And then what are the initial conditions? So what is the initial position and what is initial velocity? What are these? Right, because we're starting from rest, so that's 0. And what about initial velocity? Yep. Okay, so we have our differential equation. We have m times u double prime plus gamma times u prime plus k times u equals to g of t. And then m we computed to be 5 over 2 u double prime plus gamma, which is 0, so we don't need the second term. And the last term we have 160, u is equal to 5 cosine of omega t. Now, along with the initial conditions, u of 0 is 0 and u prime of 0 is 0. Okay, so we have the setup. Now, how would you solve this particular problem? What will be the method to use? Yeah, so to solve u of t, you would use undetermined coefficient method. That would be the easy way to go, but if you want to do variation of parameters, I think it's going to take you a while. So, but I'm not sure if it's going to take you a while, but I would go with undetermined coefficient because g of t is cosine, and we know how to find a form for the particular solution if g of t is cosine, sine, or an exponential, or a polynomial. Okay? So that's for spring mass. So any questions on these problems? Alright, so if there are no questions, we will move on to the next section. So the next section we have is, well, we're done with chapter 3, moving on to chapter 4. So chapter 4. So chapter 4 is a very short chapter we're going to work on, okay? So the title for chapter 4 is higher order linear differential equations. So higher order linear differential equations. So now we're moving on to order that are greater than 2. So we know how to solve first order, that was chapter 2. We did second order, that was chapter 3. And now chapter 4, we're going to do higher order. Alright, question? No. I think someone had a hand and I missed it.
To let you know that your voice is good.
Oh, okay. Thanks. Alright, thank you guys. Is it better now? Okay, I hope it's better. Right. So in chapter 2, like I was saying, we did first order and we learned 4 methods how to solve them. And then chapter 3, we learned second order. We solved second order by doing characteristic polynomial, and we also learned how to do non-homogeneous with second order. Now we're going to move that idea with higher order. What if now we're solving third order or a sixth order or eighth order differential equations with constant coefficient and non-homogeneous as well? So the only section we're going to cover from chapter 4 are 4.2 and 4.3. So the reason I'm not going to do 4.1 is because I think you can read that on your own. It's just talk about nth order differential equations and the theories. So just like we have a uniqueness and existence theorem for second order and first order, you compute the interval where the functions are continuous, and then you see where the initial condition will fall into. That will be the interval we have a unique solution. So same thing will apply for nth order differential equation, and the linear combination of their independent solution will form nth order solution to that. And then we also talked about Wronskian theory for the second order. You can also extend Wronskian for nth order differential equation. So you can look it up on your own. I'm not going to go over it because we're not really going to prove that, because we did the second order and I think that was good. Okay, so let's consider the nth order differential equation. So this is 4.2. So 4.2, we're going to solve higher order homogeneous differential equations with constant coefficients. Okay, so that's 4.02. And then 4.3 is again higher order differential equations with constant coefficient non-homogeneous. Okay, so that will be the non-homogeneous section. So so let's consider the following. So consider the nth order linear differential equation. So it has the following form. We have L of y, where L is a linear operator, is equal to a0 y to the nth derivative. Okay, so these exponents are derivative plus so actually I'm going to put an, okay, not a0, an, and then an minus 1. So let me just match up my coefficient with the textbook, just in case you're reading the textbook, so it will make sense. So so this is what the book does. So it doesn't use an for the first part. So I'm just going to change that coefficient, okay? So it uses a0, so that's weird, but let's use it. Let's stick to the textbook notation. a0, which is the coefficient of the nth order derivative term. So a0 y to the nth derivative plus a1 y to the n minus 1 derivative plus all the way up to an minus 1 y to the first derivative plus an y equals to 0. So I switched its coefficient a little, but it's okay, we can work with that. So this is what we call an nth order linear differential equation, linear in terms of y, where a1 all the way up to an, they're all constants, are real constants. And a0 is not 0, because we want to talk about nth order, so we want to make sure a0 is not 0. Okay. Now we're going to again assume that the solution form, so the solution form, it's going to be y equals e to the rt. Okay. So if we assume that, that means to prove this, we kind of have to differentiate this nth times, plug everything in, factor, come up with a polynomial that we know how to factor, or come up with other technique when we can't really factor to find the roots of that characteristic. Okay, so that's the idea with these higher order differential equations. Now let me illustrate this idea with examples. So suppose we want to solve the following. Okay, so let's compute the general solution. So again, I'm not doing the proof because it's the same idea as second order. You plug in the derivative second time and plug everything in. Whereas the nth differential equation, you compute the nth derivative, and it's just any real integer, and then plug everything in into this L of y. And from there, you'll see the solution has the form of an exponential e to the rt. Okay, so that's why I'm skipping the proof. So compute the general solution of let's see. So let's do y to the fourth derivative minus y equals to 0. So here we have a fourth order linear differential equation. So this is a fourth order linear differential equations, and it's homogeneous. So the usual way, we come up with its characteristic polynomial, find its roots, and those roots we write it as e to the r1, r2, r3, r4. So we're expected how many roots? 4. 4 roots. So we have r1, r2, r3, and r4. Okay, so let's proceed. So let's write out its characteristic polynomial. So the characteristic polynomial, it's going to be r to the 4 minus 1 equals to 0. Okay, so here you want to practice some of your algebraic technique where you have to know how to factor a fourth root. Do you guys remember how to factor this? So this one is, you can factor this by thinking it's a quadratic, okay? So it looks like a difference of perfect square, but the power is a fourth root, right? So I'm gonna think of it as r square, okay? So then you have, if you remember from the past, if you have r square minus 1, you would factor it into a difference of perfect square. So you have r plus 1, r minus 1. But in our case, our r square is kind of like r to the fourth. So we're going to have r squared plus 1 and r squared minus 1. I hope that makes sense. So if I factor, I have r squared minus 1 and r squared plus 1 equals to 0. So we're using the difference of perfect square, but not a square, but fourth root. I don't know if there's such a word for this, but the idea is really coming from a quadratic, and it's a difference of perfect squares, but it's a fourth root, so fourth degree, let's say that. Okay. Now, can I find the r values from this factored form? So r squared minus 1, I can factor that one more time. So that would factor into r plus 1 and r minus 1. How about r squared plus 1? Can you factor that further? So, no, right? There's no formula for sum of perfect squares. So we can't really factor, but in this course, we have complex solutions allowed. So we know r squared plus 1 will give us the complex root. So we have r squared plus 1. Leave it as it is because we're going to find complex root for that. Right, so Sadia, you have it right. So complex roots. So the first two will give us r1 is 1, r2 is negative 1. So we successfully found two of them. The other two are going to come from r squared plus 1 because complex root, we know they come in conjugate pair. So we have r3 and r4 as plus and minus I. So we have successfully found 4 roots to this fourth order differential equation. So now is the part where you state the solution for all of these roots. So we write out the solution. The solution is y equals e to the rt. So the first two are distinct real, and the last two is complex. So we're going to have solution involving exponential along with sine and cosine. So our general solution, it's going to be y equals c1 e to the r1t, that's 1t, plus c2 e to the r2t, that's negative t, plus, now c3 and c4, they're going to involve sine and cosine. So for complex root, alpha is 0, beta is 1, so we have c3 cosine t plus c4 sine of t. And there we have it. That's our solution. So let me know if you guys have questions. Does all of this make sense? Does it make sense what we're doing? Yeah, definitely. So this is the chapter you want to review tons of algebraic skills, okay? You have to remember tons of factoring. I will give you some methods for you to use how to find roots of higher degree polynomials, but you should still review factoring. I think factoring is the method where almost always it'll work. Unless there's a complex root, then we have to do it differently. and we're going to use roots of unity to go over complex roots. Okay, so I'm going to do the same problem, or maybe a different one, using another method. So let's do another problem before we do that. So here's another example. So again, let's compute the general solution. So let's solve let's do y to the third derivative plus y equals to 0. So I'll give you a few seconds to think about this and see how far you can go. Okay, so let's see what are the solutions look like for this differential equation. So this is a third order. That means we're expected to find three roots, R1, R2, and R3. And then determine, based on the roots we get, we can express the solution, see which form it is, if it's a distinct real, if it's a repeated real, or if it's complex. Okay? So let's just use the technique of factoring first. So the characteristic polynomial of this is going to be r cubed plus 1 equals to 0. Another algebra question. How do you factor this? R squared minus r plus 1. Yeah, so absolutely correct. So the formula that we're using here, so there is a formula for this. So we're using this formula. If you have, say, a cubed plus b cubed, so you're factoring two perfect cubes. So the formula is to do a plus b times a squared minus ab plus b squared. Okay, that's the formula. There's also a formula for difference of two cubes. So if you have a cubed minus b cubed, that's going to be factored into a minus b times a squared plus ab plus b squared. They're very similar, they just have a negative sign in a different spot. Okay, and then we are very familiar with the difference of two squares. That's going to be a plus b times a minus b. So these are the three formulas that I think they're very useful as far as this course. We will be using that very often. And then you can also avoid this sometimes. If the roots are complex, then you can use the roots of unity method, which we're going to cover later on. But for now, let's see if we can just use that formula. So moving on. So we have one root, R1, that's negative 1. Okay, so that's a real and distinct. Now, what about the roots for this piece? Are they real or non-real? Yeah. So let's find those roots. So r is equal to negative 1, so that's positive 1, plus and minus square root of b squared, so that's 1 minus 4ac all over 2a. So complex roots for this one. So what do you guys have? 1/2 plus and minus. So 1 minus 4, that's a negative 3, so square root of negative 3. Negative, so that would be square root of 3i over 2. Okay, so that's the root for this one. So we have R2 and R3 complex conjugate. So we have all roots we were after. So what's the solution? So the solution would look like one with exponential because one of the root is real, and the other two are complex. So we have alpha and beta. So using these roots, our general solution is going to be y equals c1 e to the negative t plus c2 e to the 1/2 t cosine of square root of 3 over 2t plus c3 e to the 1/2 t sine of square root of 3 over 2t. That would be our general solution. Now, how many initial conditions do you need to solve this particular problem? 3, right? So you would need 3 initial conditions. So 3 initial conditions to solve. So we need 3. Okay. All right. So let's do another problem. So what if we have something like this? So let's look at this one. All right. So let's pause for a few seconds, guys. My stylus is not working. Let's pause for a minute. Okay. All right. So sorry about that. I ran out of charge. Okay, so let's do another example. So suppose we want to find solution to this problem. So let's solve y to the 6th derivative minus y to the 2nd derivative equals to 0. So, So how do we do something like this? So we write out its characteristic polynomial. So we have r to the 6th minus r squared is equal to 0, right? And then from here again, looks like factoring is still gonna work. So let's go ahead and use it. So we pull out our square, so we have r to the 4 minus 1 equals to 0. So r squared will give us 2 roots, so we have repeated. So we have r1 is equal to r2, which is 0. So we have 2 repeated. And then r squared minus r to the 4 minus 1 will give us 4 more roots, but we already solved that previously. So if you look here, r to the 4 minus 1, we had 2 distinct real roots, 1 and negative 1, and then the remaining 2 were complex conjugate I. So this one, so from before we have r1, so this would call it r3, 1, and r4 is negative 1, and then r5 and r6 are complex conjugate of I. Okay, so we have all the roots. So let's look at how the solution would look like. So our general solution, it's going to be y equals So with the repeated roots, we have c1 e to the 0t, that's just 1, plus c2, make it distinct by multiplying it by t. And then the remaining ones we already know from before. We have c3 e to the t plus c4 e to the negative t plus c5. Now with the complex root we have cosine t plus c6 sine of t. So that's how the solution look like if some of the roots happen to be real and repeated. Sorry, complex and real repeated and real distinct. Okay, so any questions on this? So you see that the idea is the same as doing second order, but it's just you have many solutions, more than two, because we're working with the sixth order or fourth order, so we want linearly independent solutions of sixth order. Okay, so we have 6 linearly independent solutions, and their linear combination together forms the general solution, which we have it right here. Okay, so any questions on this? So let's look at another example. So what if you want to solve something like, say, y to the 4th derivative plus y to the 3rd derivative minus 7y to the 2nd derivative minus y prime plus 6y equals to 0. So it's a 4th order, but it has a lot of terms. So let's look at its characteristic polynomial. So the characteristic polynomial of this, it's going to be r to the 4 plus r to the 3rd minus 7r squared minus r plus 6 equals to 0. So we're expected to find 4 roots to this, right? So we're looking for r1, r2, r3, and r4. Now how do we find those roots? So can we factor this? Do we have a technique for that? No, that's illegal. Yeah. So we wouldn't really have a factoring method for this one because it has too many terms. So what we have is the rational root test. Okay, so I don't know if you guys remember this from algebra. Rational root test to find the root of a polynomial. Have you guys heard of this? Maybe magically. Okay, so Sadia says no. Okay, so to show you how the rational root tests work. So we're going to assume the roots are rational, okay? Not complex. If it's complex, then we have to do it differently. So suppose there are rational roots. So here's so this is a recall. So the rational root test. So we use rational root test to find roots of a polynomial, possible roots. So if you have a polynomial p of x, which is equal to an x to the n plus an minus 1 x to the n minus 1 plus all the way up to a1 x plus a0, okay? Where these coefficients are real numbers, then we say that the possible, so they're not really roots, they're possible roots. The possible roots for p of x, this polynomial, are as follows. It's going to be plus and minus the factors of a0, which is the constant term, divided by the factors of an. So I'm just going to put one big bracket instead of tiny ones. So these are the roots we're going to test and see if any of these are the real roots. So using this test, rational root test, we want to determine what are the roots for the one we're given. So what's a0 for this example? So 1, no, not 1. a0 is the constant term. So in this case, this is right. And then an is the coefficient of the leading term. Leading term meaning the highest power. Coefficient of the highest power, that will be right here. So that will be an. In this case, it will be a fourth. So we're going to find possible factors. So what are the possible roots? So the possible roots are plus and minus the factor of a0. So we have factors of 6. So let me write it out. a0 is 6, so the factors are 1, 2, 3, and 6. These are the factors of 6. And 1, that's an. Well, the factors of 1 is just 1, right? So there's no other factor. So my possible roots are the ratio of a0 over an. So we have 1 over 1, that's 1, 2 over 1, that's 2, 3 over 1, that's 3, and 6 over 1, that's 6. So these are the possible roots for this particular polynomial. But we have to test which one of these are the true root, if they are. So how do we test? How do we test if a value is a root?
If you're trying to find for like if check if one is a root, then you would like divide the polynomial by like by
R minus 1, right. If 1 is a root. Okay, so you can do a lot of techniques, right? You can use, so the one you suggested is kind of like the long division, right? And then we also have synthetic division to test. And we also have just plugging it in. Plugging it in and see if it's 0. So Gabriel, you got that. So we want to see if 1 is a possible root. So first I'm going to just plug it in. If it equals to 0, it's a root. If it makes the statement true, that means it's a root. Okay? So how many ways can we test? So to test, you can do it multiple ways. You can either do long division or synthetic division, if you remember how to do that. So let me just write that out. Or synthetic division. So for both of these tests, you want to make sure that the remainder is 0, if it's a root. Alright, someone had a question. Panic? Oh, these are the factors of 6. So 1 is a factor of 6, 2 is a factor of 6, 3 is a factor of 6, 6 itself is a factor of itself. Okay? And then for an we have 1, there is no factor of 1, it's just 1. So if you want to do long division or synthetic division, if the remainder is 0, so that means it's a root. Okay? Another test that you can do is just plug in. plug in the value and see if this statement is true. If this statement is true, that means it's a root. If it's not true, then it's not a root. So first I'm going to do plug in because that's simple. We can just plug it in and then see if it's equal to 0. If not, then it's not a root. So let's test 1. Let's do 1. R equals 1. So I'm going to plug into the original equation, which was r to the 4, so 1 to the 4, which is 1, plus 1 cubed minus 7 times 1 squared minus 1 plus 6. So I plug it into the characteristic polynomial, and I want to see if this is equal to 0. Is this true? So what do we have? We have, is it? Check. I think someone said yes. So 1 is a root. So we found one of the root. So we can say R1 is equal to 1. Oh, that's good. So we need 3 more to go. Now you can keep going. You can do this for next remaining roots, checking and plugging in, but I'm not going to do any more plugging in. I'm going to do synthetic division. So that way you get to see another method, alternative, if you don't want to do plug in. So let me show you how synthetic division works. Okay, so I'm going to test if r equals -1 is a root. So I'm going to test this one. So let's check. So the way I like to do synthetic division is you draw R right here, you draw a box, and then next to your root inside the box you write down all the coefficient of the polynomial in order. So the first column will be for r to the 4th, second column will be r cubed, then r squared, r to the 1, so which is r, and then the constant term. So we're going to place the coefficients right underneath these variables accordingly. So we have 1, 1, 1, 7. So 1, 1, -7, -1, and 6. So I place the coefficient over there, and now I'm going to bring down the first coefficient and multiply it with my root. So I'm going to multiply this one with -1. That gives me -1, so I replace it right here. And then I just repeat this process, and then I add them up. So 1 times -1, that's 0. And now you repeat, -1 times 0 is 0, and then you add them up, you get -7. And then -1 times -7, that's +7. Add them up, you get 6. 6 times -1, -6. Add them up. Oh, heaven Jesus, this is good. You get 0. So if the remainder is 0, it's a root, right? So we found the second root. R2 is equal to -1. So there you go, you have 2 roots. We have 2 more to go because we need 4 roots. So we tested 1 and -1. The next one you can go is 2 and then -2. So what do you guys want to test? What do you think? Should we do 2 or -2? So I'm going to go ahead and do 2. So let's test r equals 2, if that's a possible root. Let's test this one. So again, I'm going to do synthetic division. I think it's quite fun. So 2 outside the box. Inside the box, we place all the coefficients in order. If one of the coefficient is missing, we consider that as a 0. Okay. So the first one we have 1. Second we have 1. Then -7, -1, and 6. And then we just repeat this process for synthetic division. So bring down the first constant and multiply with the r value you picked, 2 times 1, that's 2. Add them up. 2 plus 1, that's 3. And now we repeat. 2 times 3, 6. Add them up, you get negative 1. And then 2 times negative 1, that's negative 2. Add them up. What do we have? Negative 3. And then negative 3 times 2, negative 6. Add them up. 0. Oh, good. Great, great, great. So we have another one. R3 is 2. One more to go. R4. So why don't you guys tell me what's R4? So what are the roots we're testing? So Gabriel says negative 3. So negative 3 is a root. So I'm going to go with what Gabriel says. We accept that. Negative 3. So there you go. So you have 4 distinct real roots. So I know how the solution looks like. It's an exponential. E to the RT, R1, R2, R3, R4. So y is equal to C1 e to the t, R1t, that's 1, plus C2 e to the negative t, plus C3 e to the 2t, and C4 e to the negative 3t. So that's the solution to this problem. How do you guys like that? No comment? Okay, you guys are very quiet. I will take that as a great. Okay, right. So yeah, so you can do plugging in if that happens to be the best thing. I sometimes don't like plugging in because if you look at the polynomial, sometimes you have 4th degree or a 6th degree. So if you're finding a 6th degree of, say, number 3, that's 3 times 3 times 3 times 3 times 3 times 3. So that's a huge number. So sometimes plugging in is not a best choice. I would go with other options. Okay, so just make sure you know other options. Yeah, but I like synthetic division. It's really nice and neat. So, and once you get the remainder 0, you know that's a root. If the remainder is non-zero, then that's not a root. So you just move on to the next value. So it's kind of fun. And the next one you can do is long division. I don't like long division much for this sort of equations because you have to keep track of your variables and the number. So it's a lot of work. So I would go with synthetic division for most part. Alright, so what are the techniques we have so far if we have a higher order polynomials to solve? Well, we do factoring. That's the first thing you want to try. And then the second thing you want to try is rational root test. If the roots you think are possibly real, then we run with rational root test. If the roots are not real, then we have to do roots of unity, because that's the test if the roots are complex. Okay, so that's another really nice method to work with. So let me just write all of that down, and then we'll stop. We'll take the quiz and call it a day. Alright, so far, what do we have? So far, to solve a higher order differential equations, we use the following. So once you write out the characteristic polynomial, try factoring. That's the best thing in life. Factoring should work 90%. Other 10%, we have other methods. Second thing, so you can choose between long division and synthetic division for the rational root test. So go with rational root test. So rational root test. So this is to find real roots. Okay, it doesn't work for complex roots, so don't try it. It's not gonna work. And then within the rational root test, you can do plug-in to test possible root, or you can do synthetic division. So I didn't go over long division, but you can always look it up. Long division, so similar to synthetic division, so I think you can figure that out. And then the third method we have is roots of unity. And this is for complex root. Actually, it works for both. So I would do factoring and then just jump to roots of unity. But it really depends on the question, so I wouldn't conclude that, so backtrack. Do rational root test, it's nice. Complex and real. So the roots of unity gives you both. It gives you complex root or it gives you real root. And then we're going to go over roots of unity next class. So just to give you a heads up, roots of unity is a method to write. So I don't know if you guys heard this in any of your previous courses. It's a method to write or to express complex polar form of a complex number. So briefly, let me tell you what do I mean. So if z, let's say z is a complex number, meaning, so z is equal to some a plus bi. So I previously used alpha plus beta I, so now I'm using a plus bi. I hope you guys are okay with that. I'm going to write this in polar form, so we have some r e to the I theta. That's the polar form of a complex number, where r is the radial distance from the origin, meaning the magnitude of z, which can be defined as the square root of a squared plus b squared. So that's just the magnitude. Of z, the complex number z. And then theta, we define it as a tangent inverse of b over a, where b is the y coordinate and a is the x coordinate, so it's y over x. Okay, so we're going to pick up from here next time, which is tomorrow. Meanwhile, we're going to stop. Let me know if you guys have questions, and then we'll proceed to the quiz. So any questions so far? How do you guys feel? So you guys seen complex numbers since you had it in the homework, so that's good. So it wouldn't be super new. So I'm glad that assignment was there. Okay, thanks Sadia for sharing that. Alright, so we'll stop here and we'll take a break for a minute.